millimeters this side, 50 millimeters this side, and this side let's take to 200 millimeters just to have some idea. So first we would have to investigate that. Now the discretization must be dependent, as we see, on the wavelength, and this is again dependent on frequency. So we have to somehow decide at which frequencies we would investigate this thing. So let us make a brief estimation. We have 200 millimeters, which is 20 centimeters. So this is something where if we consider the higher permittivity, then the frequency that is there would be something like 1 gigahertz. So let's investigate this. I mean 1 gigahertz or more, because under that this would not be a resonator supporting a resonating mode. So let us think that we have to investigate this up to 10 gigahertz. If this is the true, the wavelength in this media, in the free space, at 10 gigahertz is 3 centimeters. So we have here lambda equivalent to 30 millimeters. In the denser part, the wavelength is proportional to a square root, inversely proportional to a square root of relative permittivity. So the wavelength would be 15 millimeter. So now, if we choose the discretization step, we should obey the condition within the denser part of the area we want to solve. So for space steps, this part with the dielectric is more important. So let's say we will decide to have 15 cuts per wavelength. 15 cuts per wavelength would give us a 1 millimeter discretization brick over here. So we have established discretization. I would put down only delta x, but that's also delta y and delta z, and that would be equivalent to 1 millimeter. Now let us get to the time step. And now in order to have stable computation, it must be stable anywhere in the structure. So the bigger velocity of light, the velocity of light in the less dense part of the dielectric would be important. So then we have, let's say, let's say 1 millimeter. So we have 1 millimeter to raised. I will resort for my calculator for a moment. So what we have got is a time step which is slightly under 2 microseconds. Isn't that strange? Okay. I might made a numeric mistake, but let's stick to this number at the moment. Now the important thing I wanted to show is that if you have a problem with more dielectrics or more materials, not counting perfect conductors, the step size is given by the most dense material, the step size in space. But then you have to keep the same step size in the less dense materials. And that decreases the time step. Now, just consider that you have 100 by 200 by 50 bricks or discretization cells in which you have 6 field quantities at each: Hx, Hy, Hz, Ex, Ey, and Ez. And you have to update those in each time step, and you would have to do that for quite a long time in order to get sufficient coverage of the property of this cell. For example, to get down to 1 megahertz, you would have to do enough steps in time. So this is the greatest disadvantage of the finite difference time domain method. Again, the disadvantage is in the situation that you would get materials with different optical density or with different values of conductivity that is finite but not negligible. So if you have, for example, something which is semi-conductive or poor conductor, a little bit conductive resistive layer, then you have to decrease, to compress your discretization step in time. But the other effect of that would be that you both decrease time and space steps, and you would get a much bigger problem in resource demanding from the computer. So this is the greatest disadvantage. FDTD is very effective to solve problems when there is only one dielectric or several dielectrics that are of comparable dielectric constant. In fact, there is not much materials with very high permittivity. So dielectrics are not the main problem. But once you get partially conductive materials, the wavelength is even much smaller. And then the optical density of that material gets higher. And this would result in a very number crunching, demanding solution. So that's the weak point of finite difference time domain method, is the situation where you have quite different materials as to dielectric and conductive properties mixed in the problem. Now, your questions, please. I'd look into the chat. Okay, so this is a good time to make a 5-minute coffee break in the lecture. See you in a few minutes.